Okay. Hello, everyone. I'm Haiheng from Huazhong University of Science and Technology. And I'm going to share our work, MetaHG, Enhancing HGNN Systems Leveraging Advanced Metapath Graph Abstraction. It is an acceleration work for heterogeneous graph neural networks. The first to introduce is the heterogeneous graph. It is a special graph structure that contains multiple vertex types or edge types. For example, this figure shows a heterogeneous graph with 3 vertex types: author, paper, and conference. There is an important consumption in heterogeneous graph, a metapath. It is a sequence of vertex types that expresses the semantic relationships among different vertex types. For example, this figure shows 2 metapaths, APA and APC. APA means that two authors co-authored the paper, and APC means that one author presented a paper at a conference. The next is the heterogeneous graph neural network, HGNN. HGNN uses the metapath to capture the rich semantic and structure information in heterogeneous graph. It usually involves 4 steps. First, feature projection. It maps all vertex features into a uniform dimension. And second, semantic graph construction. It builds a semantic graph for each metapath. And third, intro-metapath aggregation. It aggregates features from numbers in the semantic graph for each metapath. And last, inter-metapath aggregation. It integrates semantic information from all semantic graphs for each target vertex. We have tested several HGNN models on different datasets and find that the performance bottleneck of HGNN lies in semantic graph construction stage. It contains matching metapath instance, constructing semantic graph, and encoding metapath instance. This figure shows the semantic graph construction and instance encoding account for over 98% of the total inference time. So our work aims to optimize this progress to improve the efficiency and performance. There exist two main types of semantic graph construction methods. They are BFS and DFS solutions. Note that the BFS and DFS refers to strategies for generating metapath instance, not the traditional graph traversal techniques. The graph solutions pre-match and store all metapath instances and use this instance to construct semantic graph and encoding. And the DFS solutions construct the semantic graph and encoding the instance at the same time as the metapath instance are matched. It matches instance directly in the original graph and encodes them to obtain embeddings and updates the semantic graph immediately. Each instance is discarded after processing. This method saves significant memory, but requires rematching instance from the original graph for each inference. It increases the matching overhead. We analyzed both the BFS and DFS solutions and find several problems. The first is the large memory consumption in BFS solutions. The BFS solutions need to store all metapath instances, since the number of metapath instances grows exponentially with the graph size and the length of metapaths. BFS solutions therefore require a quite large memory space, while the DFS solutions don't need to store any metapath instance, so it don't have such problem. The second is the construction latency. BFS solutions need to read all metapath instances from memory and construct the semantic graph with high latency. And the DFS solutions enumerate metapath instances from initial graph and construct semantic graphs, causing higher latency. The last is the redundant computations. BFS solutions performs redundant computations due to the common subpaths among Metapath instances. For example, the 1-4 in Metapath instance 141 and 143 is computed twice. The right figure illustrates these redundant computations constitute up to 42% of the instance encoding. Here is a summary of BFS and DFS solutions in these 4 aspects. Then, based on the above problems, our idea is not constructing such semantic graph, since it is too time-consuming. We use a graph to store the Metapath instance and guide the HGNN based on this graph, rather than the semantic graph. We call this Metapath graph. The right figure is a comparison of Metapath instance and the Metapath graph. We give the definition of Metapath graph. It is a compressed format of the Metapath instances. And we construct the Metapath graph from the initial graph in a copy-extend manner. We first extract the unique part of the Metapath in the initial graph and copy the repeated part to form the final Metapath graph. Such method doesn't need to traverse the initial graph, and it is much efficient. We find the Metapath graph has the following 2 characteristics. First, it is a layer-wise graph. The vertex in a Metapath graph are typically organized into several layers. Vertex in each layer connect only to the vertex in adjacent layers. It inspires us to divide the Metapath graph into layers for parallel computation. Second, its adjacent matrix is sparse block matrix with few non-zero blocks. These sparse blocks are stored separately. Such block-wise storage facilitates easier traversal over Metapath graph, since it allows for bypassing most zero blocks when accessing Metapath instance. Then, such a Metapath graph may need partitioning due to its size. Previous studies use batch partitioning that randomly divides the target vertex into batches, such that Metapath graph is divided into several parts. However, this method may lead to several problems. First, each sub-MG is still large, as we can see from the figure. Both of these 2 sub-MG is as large as the initial graph, just with a few less edges. Second, there are numerous common edges across different sub-MGs, leading to substantial redundant computations during encoding. We then propose a centralized partition method, and we partition the MG at the middle layer rather than the first layer as in the traditional batch partitioning. The centralized approach prevents excessive overlaps between sub-MGs and reduces redundant computations during encoding. We can see in the figure, each sub-MG is relatively small and the few common edges across different sub-MGs. And then, how to encode in Metapath instance based on the Metapath graph. The naive method is just traversing Metapath graph to get Metapath instance and encoding. But such method is still time-consuming. We therefore present layer-wise encoding and aggregation method based on the characteristics of Metapath graph. It first divides each sub-MG into layer-based segments Each segment is independently processed by multiple instance generation and encoding kernels. The figure shows an example of Metapath APCPA and its computational process. Such Metapath graph contains 100 computations during encoding, but by the layer-wise encoding and aggregation, only 50 computations are needed. We further present prioritized layer-wise encoding and aggregation method. For the case of special metapaths that have identical paths, we can reduce computation further. We prioritize those subgraphs involving the same path and perform only one of them to eliminate the redundant computations. In this example, the AP path and the PA path are identical. We only compute one of them, and the total computations are reduced to 39. Okay, here is our experimental platform and workloads. We use 3 HGNN models and 6 heterogeneous graph datasets. And here is the baseline of our work. The first baseline is a BFS-based HGNN system, and the second is MetaNFGS. It is a DFS-based HGNN system, and the third is our MG-driven HGNN system. Results show that we can achieve 42 times and 4.5 times improvement compared to the baseline and MetaNFGS. We further tested the contributions of our 3 key techniques to the overall performance, and the results are in the figure. The naive MetaHG only applies Metapath graph ideas using the traversal method to get our Metapath instance. And we also tested the redundant computations reduction and the performance of dynamic graphs. We can reduce on average 42% and 20% computations compared to baseline and the MetaNFGS. We compared our system with the dynamic HGNN system graph MetaP and the baseline. We can achieve 44 times and 4.5 times on average improvement. Here is our summary. We conduct a thorough analysis of the workflow deficiency inherent in existing BFS and DFS-based HGNN solutions, identifying significant inefficiencies. We then introduce a novel Metapath graph abstraction that uniformly represents the structure and semantic information of our Metapath instance in a tightly compressed format, thereby streamlining the HGNN workflow for enhanced performance. We then develop MetaHG, an MG-guided HGNN system that uses layer-wise encoding and aggregation to achieve rapid inference and maintain low storage requirements. Okay, that's all for the introduction of our work. Thank you for